Mamta from BSc Chemistry on final year. Today I am here to study about carbohydrates. One of the most important classes of biomolecules is carbonates. Carbohydrates. These includes the compounds like sugar, starch, glycogens, cellulose, dextrins and gums. Although they are widely distributed both in animal and plant kingdoms, yet they are obtained many from the plants. They are formed in the plants by a process known as photosynthesis and make up about 70% of solid plant material. Carbohydrates play a vital role in our daily life. They provide us with three basic necessities of life: food, clothing, and shelter. Classification Classical definitions. The name of carbohydrates was originally given to the classes of compound containing only carbon, hydrogen and oxygen. The hydrogen and oxygen being present in the same ratio as in water, these compounds could therefore be represented by the general formula CxH2O. Limitation of the old definition. The above definition could not survive long due to the following reasons. A number of compounds such as Rahmans and deoxyribose are known, which are carbohydrates by their chemical behavior but cannot be represented as hydrates of carbon. There are other substances like formaldehyde and acetic acid which do not behave like carbohydrates but can be represented by the general formula CxH2O. Carbon is not known to form hydrates. Modern definition. Carbohydrates are defined as the polyhydroxyaldehyde or polyhydroxyketone or substance which gives these on hydrolysis and contain at least one chiral carbon atom. It may be noted here that aldehydic and ketonic groups are carbohydrates are not present as such but usually exist in combination with one of hydroxyl group of the molecule in the form of homolytical and the helimetals respectively. Classification of carbohydrates. Carbohydrates are also known as saccharides. These are classified into the following three classes depending upon their behavior toward hydrolysis. Monosaccharides. These are the simplest carbohydrates which cannot be hydrolyzed to similar molecules. Their general formula is CH2O and where N is the value of 3 minus 8. 3 to 8. Oligosaccharides. These are carbohydrates which on hydrolysis gives 2 to 10 molecules of monosaccharides. Depending upon the number of monosaccharides molecule actually obtained upon hydrolysis, they are further classified as di, tri and tetrasaccharides, etc. For example, disaccharides, carbohydrates which upon hydrolysis given two molecules of the same different monosaccharides are called disaccharides. For example, sucrose, maltose, lactose, etc. Their general formula is C12H12O11. Trisaccharides, carbohydrates which on the hydrolysis gives three molecules of the same or different monosaccharides are called trisaccharides. For example, raffinose upon hydrolysis gives one molecule each of glucose, fructose and galactose. Their general formula is C18H32O16. Tetrasaccharides, carbohydrates which upon hydrolysis gives four molecules of the same or different monosaccharides are called tetrasaccharides. For example, Stracciose upon the hydrolysis gives one molecule each of glucose and fructose and two molecules of galactose. Their general formula is C24H42 and O21. Polysaccharides, carbohydrates which upon the hydrolysis gives a large number of monosaccharides molecules are called polysaccharides. The most commonly occurring polysaccharides are starch, cellulose and glycogen. Their general formula is C6H10O5N, where N is 100 to 3000. Sugar and non-sugar carbohydrates are further classified as sugar and non-sugar. All the monosaccharides are oligosaccharides, are crystalline solids soluble in water and sweet in taste. These are collectively called sugars, and the polysaccharides, on the other hand, are amorphous solids insoluble in water and tasteless, and thus are called non-sugars. Reducing and non-reducing sugar or carbohydrates. Carbohydrates are also classified as reducing and non-reducing sugar. All those carbohydrates which contains aldehydic and ketonic group in the homoacetical and hemikettle form and reduced tolerance reagents or Falling's solution are called reducing carbohydrates or sugars, while other which do not reduce these reagents are called non-reducing carbohydrates or sugars. All monosaccharides, whether aldose or ketose, are reducing sugars. Disaccharides such as sucrose, in which the two monosaccharides units are linked through their reducing centers, that is aldehydic or ketonic groups, are non-reducing, while other in which these groups are in the homoacetical and hemikettle form are reducing sugars. However, all polysaccharides are non-reducing carbohydrates. Let us now briefly discuss each one of these classes of carbohydrates. Classification of monosaccharides. As stated above, monosaccharides are the simplest carbohydrates which cannot be hydrolyzed to the smaller molecules. They contain 3 to 7 carbon atoms. There are about 20 monosaccharides which occur in the nature. These are of two types. Aldose monosaccharides containing an aldehyde group are called aldose. Since the aldehyde group is monovalent, therefore it is always present at the one end of the carbon chain, that is at C1. Ketones monosaccharides containing a keto group are called ketose. Since the keto group is divalent, it can be present anywhere along the carbon chain. However, in all the natural occurring keto group is always present at a carbon atom next to the terminal carbon, that is at C2. Aldose and ketose are further classified as trioses, tetroses, pentoses, hexoses, septoses, etc. according to as they contain 3, 4, 5, 6, 7, etc. carbon atoms respectively. The classification of monosaccharides as summarized in table. Nomenclature. Monosaccharides are better known by their common names, which in most cases end in the suffix "one", for example, ribose, glucose, fructose, etc. Thus, IUPAC name of monosaccharides are seldom used. For example, the simplest above, aldose containing 3 carbon atoms, is generally known by its common name glyceroaldehydes and seldom by its IUPAC name 2,3-dihydroxypropanol. Similarly, the simplest ketose is better known by its common name is dihydroxyacetone and seldom by its IUPAC name 1,3-dihydroxypropanol. However, monosaccharides containing more than 4 chiral carbon atoms, that is allidoheptose, allidooctose, etc., are named by IUPAC system using 2 or more prefixes derived from the lower sugars. Thus, 1 chiral carbon, glycorio, 2 ethyrio, 3 riboxylohexo, 4 altro, gluco, and guloiodoglycotio. The IUPAC name of the sugar is then obtained by giving the prefix denoting 4 chiral carbon which occurs adjacent to the C1 and C2 proceed by another prefix denoted by the next group chiral carbon atom. For example, d-erythro-d-glucoso-octoso. In IUPAC name system, ketones are named by means of suffix "-ulose" proceeds by a prefix indicating the total number of carbon atoms in the chain. The position of the keto groups is usually indicated by a number. For example, fructose is a 2-hexulose. The configuration of ketose is indicated by a prefix derived from the conjugation of chiral carbon atoms in the corresponding aldose. For example, D-fructose and D-ribonic hexulose and D-sorbose is called D-xylohexulose. Deoxy sugar in which one or more hydroxyl group are replaced by the hydrogen atoms are called deoxy sugars. In the common system, deoxy sugars are named by adding the prefix deoxy along with the number of the carbon atom to the common name of the aldose or ketose. For example, 3-deoxyribose, L-rhamnose, L-fructose, L-ditoxins. In IUPAC system, deoxy sugar are named by adding two prefixes to the name of the aldose and ketose containing the total number of carbon atoms in the chain. The name begins with the prefix deoxy along with the locant followed by the prefix representing the system of chiral carbon atom as shown below. Above. Since most of the earlier work of monosaccharides was carried out with hexose, that is glucose and aldose becomes and fructose, ketonoxose. Therefore, we will start our study monosaccharides with these two representative compounds. It may, however, be added here what is the true about glucose is also true about other aldohexose, and what is true about the fructose is also true about other ketones. D-glucose, dextrose and gap sugar C6H12O6. Glucose is the most widely distributed monosaccharide. It occurs free in large quantities in ripe grapes, and there is why it is called grape sugar. It is also occurs in honey and most of the other sweet fruits. It also be present in the human blood. In the combined state, it occurs a glycosides, disaccharides, and polysaccharides. Preparation of D-glucose. Laboratory preparation. In the laboratory, glucose is prepared by the hydrolysis of sucrose or cane. When hydrolyzed is sucrose, then glucose and fructose is formed as a product. Manufacture. Sucrose is hydrolyzed by heating with dilute HCl or H2SO4 and 90% alcohol. When a mixture of glucose and fructose is obtained, glucose being almost insoluble in alcohol separate out on cooling while fructose remains in the solution. On a commercial scale, glucose is prepared by the hydrolysis of starch with hot dilute mineral acids, the chief sources of starch, and rice, maize, a potatoes starch hydrolyzed, then glucose is formed as a product. After hydrolysis, the reaction mixture is neutralized with chalk and filtered. The filtrate is decolorized with animal charcoal and concentrated under reduced pressure when glucose crystalline out. Physical properties of D-glucose. Glucose is a crystalline white solid with melting point 419 Kelvin. It is a highly soluble in water but sparingly soluble in alcohol and insoluble in ether. It is optically active and It is dextrorotatory and hence the name of dextrose. It is about 3/4 as sweet as sucrose. Chemical properties of D-glucose. D-glucose is a typical monosaccharide. It gives a reaction of both aldehydic and alcoholic groups. In order to discuss these reactions, glucose may be simply represented as the open chains pentahydroxyaldehyde as shown below. Some important reactions of glucose are discussed below. Reactions of aldehyde group. Glucose gives the usual reactions of aldehyde. However, it does not respond to Stich's reagents test and also does not form addition compound with a saturated solution of sodium bisulfate. Reaction with hydrogen cyanide. Glucose forms a cyanohydrin with hydrogen cyanide. Reaction with hydroxylamine. Glucose gives glucosoxime. When glucose is treated with hydroxylamine, then glucosoxime is formed as a product. Reaction with the phenylhydrazine. Glucose reacts with the 1 mole of phenylhydrazine to form glucose phenylhydrazone, then oxazone formation. However, if excess of phenylhydrazine is used, the reaction proceeds further to yield it as a crystalline product called oxazones, which contains 2 phenylhydrazine residue per molecule of glucose, while the third molecule of reagent is converted into aniline and ammonia. It may be pointed out here is ozone formation is not only a characteristic reaction of reducing carbohydrates, but it is also by all alpha hydroxyaldehydes and alpha hydroxyketones that is general. Further, during ozone's formation, the stereochemistry about carbon-2 chiral carbon atom of an aldose is destroyed without affecting the configuration of the rest of the molecule. Fischer's mechanism. Emil Fischer, who first prepared ozone, explained the mechanism for its formation as follows. The first moles reacts with the usual manner expected of an aldehyde. The second molecule oxidizes the secondary alcoholic group to the ketonic group, and the third mole reacts with the keto group thus generated to form the ozone as shown below. Limitation of the Fischer mechanism. The above mechanism, however, suffers from the following defects. It does not explain why phenoxyhydrazine, which is a strong reducing agent, act as an oxidizing agent in the second step, the above mechanism. It is not explained why the first 2 carbon atoms are involved in ozone formation. That is, why do the remaining hydroxyl groups not get oxidized and react further with phenylhydrazine. Modern mechanism to overcome these objections. Weigand proposed and an alternative mechanism involving amandori rearrangements. The phenylhydrazine first formed undergoes tautomerism to form a hydrogen bond 6-membered intermediate. These intermediates subsequently lose a molecule of aniline to form an aminoketone, and aminoketone then reacts further with the 2 molecules of C6H5NH2, one at the carbon oxygen group and the other at the carbon amine group to the final ozone. The mechanism is supported by the observation that when phenylhydrazine is prepared from and labeled phenyl hydrazine is treated with the ordinary phenyl hydrazine. Unlabeled oxazone is formed with the elimination of labeled ammonia. This mechanism also does not explain why the reaction stops after the addition of 2-phenyl hydrazine residues. This has however been explained on the basis of oxazone is stabilized by the chelation as shown below, and hence further reaction stops. The explanation is supported by the observation of unsymmetrically distributed hydrogens, which cannot yield oxazone capable of chelation, reacts further with the aldose forming alkazones, in which oxazone formations proceeds along the whole carbon chain of the sugar. It may be noted that the oxazone formation is generally action of the monosaccharides and alpha hydroxylaldehyde and alpha hydroxyketones. An important point about oxazone formation is that during its formation, configuration at C1 and C2 is destroyed. Evidently, any diastereomeric monosaccharides which differs from the glucose only in the configuration at C2 should give the same oxazone. For example, D-mannose, which differs from the D-glucose only in the configuration at C2, gives the same oxazone. In general, any pair of epimers which differs in configuration at C2 gives the same oxazone. Oxazone are well-defined bright yellow crystalline solid having definite shape. Therefore, oxazone are used for the identification of monosaccharides and reducing disaccharides reduction. Glucose is readily reduced catalytically or by sodium mercury amalgam and water to form hexahydric alcohol called glucoyl or sorbitol. However, on reduction with Hi in the presence of red phosphorus at 373 Kelvin temperature, it gives a mixture of N-hexane and 2-iodohexane. Oxidation. Mild oxidizing agents such as bromine water oxidized glucose to a monocarboxylic acid called gluconic acid. Strong oxidizing agents such as nitric acid, however, oxidized glucose to the dicarboxylic acid called gluconic acid. Saccharide acids, the second carboxylic acid group being formed by the oxidation of the primary hydroxyl alcoholic group. Reducing nature. Due to the case with which CHO group is glucose is oxidized to the aldehyde group. Glucose acts as a reducing agent and thus reducing tolerance reagents, Fehling solutions and the Benedict solutions. Reaction of the hydroxyl group acylation glucose reacts with the acetic anhydride to form glucose pentaacetate. When glucose is treated with acetic anhydride in the presence of pyridine, then glucose pentaacetate is formed. Formation of glucosides. Glucose reacts with the methanol in the presence of dry HCl gas to form mixture of alpha beta methyl glucosides. Formation of glucosides. When treated with the select limes, glucose forms soluble calcium glucose. Other reactions. Action of the acid. Dilute acids have no effects. However, if the glucose or any carbohydrates is heated with concentrated hydrochloric acid, it gives 5-hydroxymethyl with which further converted by hot hydrochloric acid, alevinic acid. The 5-hydroxymethyl formed above the gives violet colorations when the treated with the alpha nitrotol. The reaction before therefore forms a basis of mole search test for carbohydrates. Action of alkalis Labori deep brine 1 and alkane stains rearrangements when the glucose is treated with a concentrated solution of alkali. It first turns yellow, then brown, and finally a brown resin's mass is obtained. However, when treated with a dilute solution of an alkali, it forms an equilibrium mixture of the glucose, fructose, mannose. The reaction is called Labori-de-Brion-1 Eikenstein rearrangement. It involves the formation of 1,2-enediol as a transient intermediate in which the chirality is of C2 is destroyed due to the formation of carbon double bond. This unstable intermediate then changes into a mixture of three monosaccharides as shown below. The same equilibrium is obtained even if the starts with D-mannose to D-fructose. It is probably of this isomerization that fructose reduces tolerance reagents and failing solutions even though it does not contain an CH group fermentation. The enzymes present in the yeast readily brings about the fermentations of the glucose to ethyl alcohol. Open chain structure of D-glucose. The structure of D-glucose is discussed the under subheads. Open chain structure. The open chain structure of glucose follows from the following discussion. Molecular formula of D-glucose. Glucose is determined from the analytical data and molecular weight determination is C6H12O6. Presence of aldehyde group in the glucose reacts with the HCN to form the cyanohydrin with the hydroxylamine to form the oxime and with equimolar amounts of phenylhydrazine to form the phenylhydrazine zone. All these reactions suggest the presence of the carbonyl group in the glucose. On mild oxidation with bromine water, glucose gives gluconic acid and an acid contains the same number of carbon atoms as glucose. These reactions suggest that the carbonyl group present in glucose must be aldehydic group. Presence of a 5 hydroxyl groups when treated with the acetyl chloride or acetic anhydride glucose forms pentacetate. Thus, glucose contains 5 hydroxyl group. Further, since glucose does not lose water readily, each hydroxyl group must be present on a different carbon. The presence of the 5 hydroxyl groups and one aldehydic group, the glucose, is further confirmed by the fact that glucose on reduction with with sodium amalgam and the water gives sorbitol, which forms a hexaacetane on treatment with the acetic anhydride. Presence of one primary alcoholic group. Glucose on oxidation with nitric acid gives glucuric acid and dicarboxylic acid containing the same number of carbon atoms as glucose. One of the carboxyl group in glucuric acid must have been produced by the oxidation of aldehydic group and the other must have been obtained by the oxidation of primary alcoholic group. Thus, one of the 5 hydroxyl group is present in glucose must be primary alcoholic group. Presence of straight chain of carbon atoms. Glucose on the reduction with HI and red phosphorus with at the 373 Kelvin temperature gives a mixture of N-hexane and 2-iodohexane. This indicates the 6 carbon atoms in glucose are arranged in the straight chain. The further confirmed by the fact that glucose cyanohydride on hydrolysis and subsequent reduction with Hi and red phosphorus give 1-heptanoic acid. From, from the above discussion, it is follows that glucose contains aldehyde group and 5 hydroxyl groups, out of which one is primary and a third is a chain of 6 carbon atoms. Further, since the aldehyde group is monovalent, it must be present at the end of the chain, keeping in view these facts that the tetravalency of carbon. The following open chain structure was proposed for glucose. The above structure of glucose is confirmed by its oxidation with HiO4, which consumes 5 moles of HiO4 and produces 1 mole of formaldehyde and 5 moles of formic acid is shown below. Configuration of D-glucose. The open chain structure of glucose contains 4 chiral atoms. Therefore, it should exist in 2 to the power 4 is equal to 16 optically active stereomeric isomeric forms. All these 16 stereoisomers are known and exist as 8 pairs of enantiomers, 8 belonging to the D series and 8 to the L series. These in the facts corresponds to the D negative and L forms, D and L form of allose, maltose, glucose, mannose, glucose, iodose, galactose and talose. Out of these 16 stereoisomer, one is D-glucose and other is the enantiomer glucose. The rest 14 being diastomers of D-glucose. However, there would be no mesoforms since the two ends of molecule are dissimilar. The absolute configuration of D-glucose was established by Emil Fischer in 1891, who was awarded the Nobel Prize in 1902 for this work. The detail is his procedure is, however, discussed in section 2.10 under experimental proof of absolute configuration of aldose. The cross formulae of D-glucose and L-glucose is given below. D-glucose and L-glucose. D-fructose, levolose and fruit sugar. The fructose is the most important of all ketose. It occurs along with the in the form of inverted in honey, sweets, fruits. It is obtained from the its present in disaccharides and polysaccharides. Preparation of D-fructose. D-fructose is prepared in the laboratory by the hydrolysis of cane sugar or sucrose with dilute sulfuric acid. When the hydrolysis is complete, the acidic solution is neutralized with BaCO3 and the precipitated BaSO4 is removed by filtration. The filtrate is treated with the slaked lime with when calcium fructostate being less soluble gets precipitated with calcium glucosates remains in solution. Calcium fructostate is separated by the filtration suspended in water and decomposed by passing CO2 through the suspension when CaCO3 gets precipitated while fructose remains in solution. Calcium carbonate is filtered off and the filtrate is concentrated to get crystal of fructose on a commercial scale. The fructose is prepared by the hydrolysis of ilein with the dilute sulfuric acid. The excess acid is neutralized with BaOH2 when BaSO4 gets precipitated and is filtered off. The filtrate is concentrated by evaporation under reduced pressure to get crystal of fructose. Physical properties of D-fructose. Fructose is colorless crystalline solid with melting point 375 Kelvin temperature. It is sweetest of all the sugar. It is more stable, more soluble in water and alcohol than glucose. It is optically active and levorotatory, and hence the name of levolose. Chemical properties of D-fructose. Fructose is the one of important ketoaxones and has a following open chain structure. It contains one ketonic group, two primary and three secondary alcoholic groups. As such, it gives the reaction of both alcohols and ketones. Some of its important reactions as are discussed below. Reaction of the ketonic group. Reaction with the hydrogen cyanide. It reacts with the hydrogen cyanide to form fructose cyanohydrin. Reaction with the hydroxyl amine. Fructose reacts with the hydroxyl amine to form fructose oxime. Action with the phenylhydrazine. When treated with the equimolar amount of phenylhydrazine fructose forms phenylhydrazone. Oxazone formation. With excess of phenylhydrazine, fructose forms oxazone, which is identical with the obtained from glucose. Modern mechanism. The Fischer mechanism is not acceptable since phenylhydrazine, which is a strong reducing agent, has been shown to act as oxidizing agent in the second step of the above mechanism. Wind gave a more satisfactory alternate mechanism in which the initially formed phenylhydrazone undergoes amenorrheic rearrangements as shown below. Reduction. Fructose on reduction with sodium amalgam and water or catalytically gives a mixture of two stereomeric hexahydric alcohols. Reduction with the hydroiodic acid in the presence of phosphorus at 373 Kelvin temperature gives a mixture of N-hexane and 2-iodohexane. When it treated in the presence of Hi and red phosphorus at 373 Kelvin temperature. Oxidation. It is not oxidized by mild oxidizing agent like bromine water. Strong oxidizing agent like concentrated HNO3 oxidizes fructose to give a mixture of three acids, each containing lesser number of carbon atoms. Reducing nature. Fructose, unlike simple ketones, reducing filling solution and tolerance reagents. This is due to the reason that the under alkaline medium of these reagents. First, fructose undergoes the Lebesgue-Hurin-Van Ekenstein rearrangement to form an equilibrium mixture of glucose, fructose, and mannose. Gluco- Glucose and mannose thus produced bring about the reduction of these reagents. Reaction of hydroxyl group. Acylation. When treated with the acetic anhydride, it forms fructose and pentacetate. Action with the methyl alcohol. Formation of the methyl fructose. It reacts with the methyl alcohol in the presence of dry hydrogen chloride to form a mixture of two isomeric alpha beta methyl fructosides. Formation of fructoesters, fructostates. When treated with the slacked lines, fructose forms insoluble calcium fructostates. Other reactions. Action with acid. When heated with the concentrated HCl, fructose forms levanic acid. Action with alkalis. On warming with dilutes alkalis, fructose like glucose undergoes laboratory de Bruin van Engelstein rearrangement to give an equilibrium mixture of glucose, fructose, and mannose. Fermentation, like glucose, fructose, also undergoes fermentation by enzymes. Jam is present in the yeast to form ethyl alcohol. Open chain structure of D-fructose. Molecular formula of fructose as determined from the elemental analysis and molecular weight determination is C6H12O6. Presence of ketonic group. Fructose reacts with the hydrogen cyanide to form a cyanohydrin with the hydroxylamine to form and an oxymes with equimolar amount of phenylhydrazine to form the phenylhydrazone. All these reactions suggest that fructose contains a carbonyl group. Fructose on oxidation with nitric acid gives a mixture of trihydroxyglucataric acid, tartaric acid, and glycolic acids, each of which contains a lesser number of carbon atoms than fructose. Thus, this suggested that the carbonyl group present in the fructose is a ketonic group. The presence of the ketonic group in the fructose is further confirmed by the fact that fructose is not oxidized by the bromine water. Presence of the 5-hydroxyl group. 5-hydroxyl group when fructose reacts with acetic anhydride to form the fructose pentaacetate. This shows the presence of 5-hydroxyl group in the fructose. Further, the since fructose does not lose water easily, each hydroxyl group must be present on a different carbon atom. Presence of the straight chain of 6 carbon atom. Fructose on reduction with the hydrodic acid and the red phosphorus acids. Red phosphorus at 373 Kelvin temperature gives a mixture of N-hexane and 2-iodohexane. This indicates that the 6 carbon atoms are in straight chain. Position of the ketonic group. Fructose cyanohydrin gives on the hydrolysis gives a hydroxy acid with which the reduction upon reduction with Hi and red phosphorus at 373 Kelvin temperature yields 2-methyl 2-methyloxanic acid, and these reactions suggest that the 6 carbon atoms in fructose are present in the straight chain and the ketonic group is present at the position 2. In the light of the above facts and keeping the view of tetracovalency of carbon, the following open chain structure can be written for the fructose. Configuration of D-fructose. The open chain structure of the fructose contains 3 carbon atoms. Therefore, the number of stereoisomers possible is 2 to the power 3 is equal to 8. The naturally occurring fructose is known as the 8 stereoisomer. Its configuration was based upon the fact that fructose forms a sum of osazone as glucose. Since osazone formation involves only C1 and C2 carbon atoms, therefore the configuration of C3, C4, C5 in the both glucose and fructose must be the same. The configuration of fructose is shown in structure 1 and 2. So, thanks for watching. Thank you guys.